Picture yourself standing in the Arizona desert at night. The air is cold and still, carrying the faint smell of sage and dust. Above you, the Milky Way stretches across the sky like a river of frozen light, and if you stand long enough, you begin to feel what every human being who has ever looked upward has felt. The sense that the universe is old, quiet, and fundamentally stable. The stars have always been there. The darkness between them has always been there. The cosmos, for all its vastness, seems like something you could almost trust. That impression is one of the most dangerous assumptions in all of physics. In April of 2024, a collaboration of more than 900 scientists from institutions across 5 continents released a set of measurements so precise, so carefully checked, and so deeply strange that if they hold up under future scrutiny, they will require us to abandon the standard model of cosmology entirely. Not adjust it, not refine it, abandon it. The framework that has governed our understanding of the universe for more than 25 years, the framework that won Nobel Prizes and predicted observations with astonishing accuracy, may be fundamentally wrong about the most important component of reality. The component in question is dark energy. You have heard the term. You have probably heard that dark energy makes up roughly 68% of everything that exists, that it is responsible for the accelerating expansion of the universe, that it is one of the great mysteries of modern physics. What you may not have heard is that physicists have been operating for decades under a quiet assumption, an assumption so embedded in the mathematics that most researchers stopped questioning it long ago. The assumption was this: dark energy is constant. It does not change. It does not evolve. It sits there, uniform and eternal, the same yesterday as it will be 1 trillion years from now. The DESI collaboration just found evidence that this assumption is wrong. The Dark Energy Spectroscopic Instrument, mounted on a telescope high in the mountains of Arizona, has spent years mapping the positions of millions of galaxies with a precision that borders on the absurd. By measuring how light from those galaxies has been stretched by the expansion of space, DESI can reconstruct the history of cosmic expansion going back more than 11 billion years. And when the collaboration's scientists plotted that history, when they traced the curve of how fast the universe has been growing at different epochs, they found something that should not be there. The curve is the wrong shape. If dark energy were truly constant, the expansion history would follow a specific predictable path. The equations of general relativity, combined with the assumption of a cosmological constant, produce a clean mathematical function that describes how the universe should have grown over time. That function has been tested and verified for a quarter century. It is the backbone of modern cosmology, and the DESI data, drawn from the most comprehensive survey of galactic redshifts ever assembled, suggests that the actual expansion history deviates from that function. The deviation is subtle. It is not screaming at us from the data, but it is persistent, and it points in a direction that makes cosmologists deeply uncomfortable. Dark energy appears to be weakening, not by a lot, not in a way that would be obvious to casual observation, but if the DESI results are correct, the density of dark energy in the universe today is lower than it was billions of years ago. The force that is pushing the cosmos apart, the mysterious pressure that dominates the energy budget of all existence, is not a constant. It is a field. It is changing. And if that is true, then almost everything we thought we understood about the fate of the universe needs to be reconsidered. Tonight, if these slow explorations help you drift or think, consider tapping that like and subscribe button. It costs nothing, it helps the channel exist, and it ensures that journeys like this one continue. Now let us begin. The story of dark energy is, at its core, a story about embarrassment. Physicists do not like to admit this, but the standard cosmological model, for all its predictive success, has always rested on a foundation of profound confusion. The confusion is not about whether dark energy exists. The evidence for cosmic acceleration is overwhelming, drawn from multiple independent lines of observation. The light curves of distant supernovae, the pattern of temperature fluctuations in the cosmic microwave background, the clustering statistics of galaxies across billions of light years. Something is pushing the universe apart faster and faster. That much is certain. The confusion is about what that something actually is. When Albert Einstein first formulated general relativity in 1915, he introduced a term into his equations that he called the cosmological constant. He added it for a specific reason. Einstein believed, as most scientists of his era believed, that the universe was static. It did not expand, it did not contract, it simply sat there, eternal and unchanging. The problem was that his own equations refused to cooperate. Without the cosmological constant, general relativity predicted that the universe should either be expanding or collapsing. A static cosmos was unstable, like a pencil balanced on its tip. So Einstein added the term. He called it lambda. It represented a kind of intrinsic energy woven into the fabric of space itself, a pressure that exactly balanced the attractive force of gravity and held the cosmos in equilibrium. The universe, in this picture, was a delicate balancing act, poised forever between expansion and collapse. Then Edwin Hubble looked through a telescope and discovered that the universe was expanding after all. The galaxies were moving away from each other. The cosmos was not static, it was growing. Einstein reportedly called the cosmological constant his greatest blunder. He had invented a term to solve a problem that did not exist, a term that seemed mathematically ugly and physically unnecessary. For the next 7 decades, lambda was largely forgotten. Cosmologists built models of an expanding universe without it, and those models seemed to work just fine. Then, in 1998, 2 independent teams of astronomers made a discovery that would reshape physics forever. They had been studying a particular kind of stellar explosion called a type Ia supernova. These explosions are useful because they are standardizable. By measuring certain properties of the light curve, astronomers can determine how intrinsically bright each supernova is, which means they can use the apparent brightness to calculate the distance. Type Ia supernovae became cosmic yardsticks, allowing researchers to measure distances to galaxies billions of light-years away. What the 2 teams found was that the most distant supernova were fainter than they should have been. Not by much, just a little. But the discrepancy was consistent, and it pointed in a troubling direction. The only way to explain the dimness was to conclude that the distant galaxies were farther away than expected, which meant that the expansion of the universe had been slower in the past than it is today. The universe is accelerating. Let that settle for a moment. Not just expanding, accelerating. Whatever force drives cosmic expansion is not fading with time, as you might expect from the momentum of an ancient explosion. It is growing stronger. Something is pushing, and the push is getting more insistent as the eons pass. The teams published their results. The physics community was stunned. And then, almost immediately, theorists reached for the only tool they had that could explain such a phenomenon: Einstein's cosmological constant. The term that he had abandoned as a blunder turned out to be the only mechanism in existing theory that could produce cosmic acceleration. If space itself contains a fixed amount of energy per unit volume, then as the universe expands and new space is created, the total dark energy increases while the total matter spreads thinner. Eventually dark energy dominates, and because dark energy exerts a kind of negative pressure, the gravitational effect is repulsive rather than attractive. The universe accelerates. It was elegant. It was economical. It fit the data. And it became the foundation of what cosmologists now call the lambda CDM model, the standard cosmological model that has governed the field for a quarter century. Lambda represents the cosmological constant. CDM stands for cold, dark matter. Together, they form the 2 great mysteries of modern physics, the twin anchors of a universe that is mostly invisible and deeply strange. But there was a problem. A catastrophic, humiliating, conceptually devastating problem. Physicists could calculate, using the principles of quantum field theory, how much vacuum energy there should be. Empty space, according to quantum mechanics, is not truly empty. It seethes with virtual particles flickering in and out of existence, with quantum fluctuations that contribute a non-zero energy to the vacuum. The calculation is straightforward, at least in principle. You add up the contributions from all the quantum fields in the standard model, and you get a number. The number is wrong by a factor of 10 to the 120. Stop and feel the weight of that. Not 10, not a million, not a billion. The theoretical prediction for vacuum energy is roughly 120 orders of magnitude larger than the observed value. If you were trying to predict the mass of an elephant and your calculation gave you something heavier than the observable universe, you would know that your theory was broken. This is worse. This is the worst prediction in the history of science. And yet the cosmological constant works. Lambda fits the data. The acceleration is real. This is the dirty secret at the heart of modern cosmology. The framework that we use to describe the universe depends on a quantity that we cannot calculate from first principles, that we can only measure empirically, and that our best theories predict incorrectly by a margin so vast that it defies comprehension. The cosmological constant is not a triumph of physics. It is a placeholder for our ignorance. And that placeholder, the assumption that lambda is truly constant, is exactly what the DESI collaboration has now called into question. To understand what DESI found, you first need to understand what DESI is. Picture a telescope, not an optical telescope pointed at individual stars, but a survey instrument designed to harvest data from the cosmos at an industrial scale. The DESI instrument is mounted on the Male telescope at the Kitt Peak National Observatory in Arizona, a 4-meter mirror that has been gathering light from the universe since 1973. But DESI itself is new. It began operations in 2021, and it represents one of the most ambitious attempts in the history of astronomy to map the three-dimensional structure of the cosmos. The instrument works by capturing light from thousands of objects simultaneously. Embedded in its focal plane are 5,000 tiny robotic positioners, each one capable of aiming a fibre optic cable at a specific point in the sky. These fibres feed light into spectrographs that break the light into its component wavelengths, producing detailed spectra for each target. By analysing those spectra, astronomers can determine the redshift of each galaxy, which tells them how much the universe has expanded since the light left that galaxy. The result is a three-dimensional map. Each galaxy becomes a point in space, its position determined by its coordinates on the sky and its redshift-derived distance. Assemble millions of such points, and you begin to see the large-scale structure of the universe. The filaments and walls and voids that form the cosmic web, the scaffolding on which all visible matter is hung. But DESI is not just mapping structure for its own sake. The collaboration is hunting for something far more subtle, the imprint of sound waves from the early universe. This sounds strange, but it is real. In the first few 100,000 years after the Big Bang, the cosmos was a dense, hot plasma of particles and radiation. Sound waves travelled through this plasma, pressure waves generated by tiny fluctuations in density that had been seeded during cosmic inflation. When the universe cooled enough for atoms to form, the plasma became transparent and the sound waves froze in place. The pressure oscillations stopped, but they left a mark. The distance that a sound wave could travel during those early epochs is calculable. It depends on the physics of the plasma and the age of the universe at the moment of freezing. That distance turns out to be about 500 million light-years in today's terms, after accounting for cosmic expansion. And because galaxies tend to form along the overdense regions of the primordial plasma, there is a slight statistical preference for galaxies to be separated by that characteristic distance. This is called the Baryon Acoustic Oscillation Scale. It is a standard ruler. Just as type Ia supernovae serve as standard candles, allowing distance measurements based on brightness. The Baryon Acoustic Oscillation Scale serves as a standard ruler, allowing distance measurements based on geometry. If you know that a certain pattern in the galaxy distribution should have a specific size, and you measure how that pattern appears at different redshifts, you can calculate how the universe has expanded over time. DESI's first major data release, published in April 2024, contains redshifts for more than 6 million galaxies spanning a range of cosmic history from about 700 million years after the Big Bang to the present day. By analysing the Baryon acoustic oscillation signal at multiple redshifts, the collaboration reconstructed the expansion history of the universe with unprecedented precision. And the expansion history does not match the cosmological constant. Let me put that in perspective. The standard lambda CDM model, with its assumption of a constant dark energy density, predicts a specific relationship between redshift and the Baryon acoustic oscillation scale. At every epoch in cosmic history, the model tells you exactly how large the standard ruler should appear. DESI measured the ruler at multiple epochs. The measurements should have fallen along a smooth curve consistent with lambda CDM. They do not. The deviations are subtle. They are within the range where random statistical fluctuations could potentially explain them. But when the DESI team combined their data with other cosmological probes, Including observations of the cosmic microwave background from the Planck satellite and supernova measurements from multiple surveys, the evidence grew stronger. In the technical language of the field, the data prefer a model in which dark energy is not constant, but is described by an equation of state parameter that evolves with time. The equation of state, designated by the letter W, describes the relationship between the pressure and density of dark energy. For a cosmological constant, W equals -1. It is fixed, eternal, unchanging. But the DESI data, when analysed in combination with other observations, suggest that W was closer to -1 in the past and is moving away from -1 today. Dark energy is getting weaker, not dramatically, not in a way that threatens the universe with imminent collapse. The effect is gentle, playing out over billions of years. But the trend is there, visible in the data at a statistical significance that cannot be easily dismissed. If confirmed, it means that dark energy is not a cosmological constant. It is not a fixed property of the vacuum. It is a dynamic field, evolving over cosmic time, behaving in ways that lambda cannot explain. The implications are profound. A cosmological constant is simple. It has no degrees of freedom, no moving parts. It is either there or it is not. A dynamic dark energy field, by contrast, is a new ingredient in physics. It has parameters that must be explained. It has a physical origin that must be identified. It opens the door to a category of theoretical models that have lurked at the edges of cosmology for decades, but have never been required by the data, until now. The simplest such model is called quintessence. The name is borrowed from ancient philosophy, from the fifth element that Aristotle believed made up the celestial spheres. In modern physics, quintessence refers to a scalar field that permeates all of space, similar in some ways to the Higgs field but with different properties. The quintessence field carries energy, and as the universe expands, the field slowly rolls down a potential energy slope, like a ball rolling down a shallow hill. The crucial difference between quintessence and a cosmological constant is that quintessence can change. The energy density of the field depends on its position along the slope, and as the field rolls, that position changes. The effective dark energy evolves. If the DESI results are correct, we may be living in a quintessence universe. But quintessence is not the only possibility. A weakening dark energy could also arise from modifications to gravity itself, from extra dimensions compactified in ways that affect cosmic expansion, from interactions between dark energy and dark matter that cause energy to flow between them. The landscape of theoretical alternatives is vast and largely unexplored. For a quarter century, cosmologists had no reason to explore it. The data were consistent with a cosmological constant. Lambda worked. The models that invoked quintessence or modified gravity were interesting mathematical exercises, but they were not required by observation. Now they might be. Now, for the first time in the history of dark energy research, the data are pointing away from the simplest assumption. The universe, it seems, is not content to be described by a single fixed number. Something more complicated is happening, something that requires new physics. And here is the part that keeps cosmologists awake at night. We do not just have a dark energy problem, we have a cascade of tensions. The DESI results do not exist in isolation. They arrive in a field already riven by discrepancies, by measurements that refuse to agree, by hints that the standard model is fraying at the edges. The most famous of these is the Hubble tension, a disagreement about the current expansion rate of the universe that has persisted for years and resisted every attempt at resolution. The expansion rate is measured by a number called the Hubble constant, designated h0. It tells you how fast the universe is expanding today, how many kilometers per second a galaxy recedes for every megaparsec of distance between you and it. There are two fundamentally different ways to measure this number. One method uses the early universe. You take observations of the cosmic microwave background, the afterglow of the Big Bang, and you use the standard cosmological model to extrapolate forward to the present day. The Planck satellite measured the CMB with exquisite precision, and when you run the numbers through lambda CDM, you get a Hubble constant of about 67.4 kilometers per second per megaparsec. The other method uses the late universe. You measure the distances and velocities of galaxies directly, using standard candles like Type Ia supernovae and Cepheid variable stars. This is how Edwin Hubble first discovered the expansion of the universe. Modern measurements using this technique led by teams like the one supervised by Adam Rees at Johns Hopkins, consistently give a Hubble constant of about 73 kilometers per second per megaparsec. The difference is roughly 8%. That might not sound like much, but the measurements are precise enough that the discrepancy is statistically significant at the 5 sigma level. In physics, 5 sigma is the threshold for discovery. It means the probability of a random fluctuation explaining the difference is less than 1 in a million. The early universe and the late universe are telling us different things about the expansion rate. For years, cosmologists hoped that the tension would be resolved by some subtle systematic error, some calibration issue in the distance ladder, or some underestimated uncertainty in the CMB analysis. But every attempt to find such an error has failed. The discrepancy persists. Multiple independent teams using different methods get the same split. Early universe measurements cluster around 67. Late universe measurements cluster around 73. The DESI results add a new piece to this puzzle. If dark energy is evolving, if it was stronger in the past and is weaker now, then the expansion history of the universe is different from what lambda CDM predicts. And a different expansion history could in principle affect the inferred Hubble constant from early universe observations. Some researchers have argued that a dynamic dark energy could help resolve the Hubble tension, reconciling the early and late measurements by changing the cosmic timeline. Others are less sure. The models that reduce the Hubble tension often introduce new tensions elsewhere. The universe is not cooperating with our desire for a simple fix, but the point is this. The DESI results arrive at a moment when the standard cosmological model is already under stress. They are not a lone anomaly. They are part of a pattern, a growing collection of hints that lambda CDM, for all its success, may be approaching the end of its useful life. This is how science works, if you zoom out far enough. Every paradigm has its triumph, its consolidation, and then its slow accumulation of puzzles and tensions that eventually force a revolution. Newtonian gravity explained the solar system until Mercury's orbit refused to comply, and Einstein was needed. The Bohr model explained the hydrogen atom until the helium atom refused to comply, and quantum mechanics was needed. Lambda CDM has explained the cosmic microwave background and the large-scale distribution of galaxies with stunning precision. But the precision is now so high that the cracks are visible, and the cracks may be telling us something. In the mountains of Arizona, the robotic fibers of DESI continue to move. Every night, weather permitting, the instrument captures spectra from thousands of new galaxies. The survey is designed to run for 5 years, mapping tens of millions of objects, building a dataset that will dwarf the current release. By the time the full survey is complete, the statistical uncertainties will shrink. The deviations from lambda CDM, if they are real, will either grow more significant or fade into the noise. Cosmologists around the world are watching. They are running simulations, testing models, looking for the theoretical framework that could explain what the data are showing. Some are skeptical. They point out that the DESI evidence for evolving dark energy is not yet conclusive, that it could still be a statistical fluctuation, that we have been fooled by tantalizing hints before. The history of physics is littered with anomalies that promised new physics and then evaporated under further scrutiny. But others are excited. They see in the DESI results the first real evidence that the dark energy problem has a solution, that lambda is not the final word, that there is something out there in the vacuum of space that we do not yet understand. The cosmological constant was always a placeholder, a term shoved into the equations because nothing better was available. If it is now giving way to something richer, something that evolves and changes and has a physical origin we can study, then cosmology has entered a new era. The stakes could not be higher. The nature of dark energy determines the fate of the universe. In a lambda-dominated cosmos, the expansion continues forever, accelerating into an eternity of darkness and cold. Galaxies recede beyond our horizon, stars burn out, black holes evaporate. The universe ends not with a bang, but with an endless, ever more diluted whimper. But if dark energy is not constant, if it can change, then other fates become possible. A dark energy that grows stronger over time could lead to a scenario called the Big Rip, in which the accelerating expansion eventually tears apart galaxies, then solar systems, then planets, then atoms. A dark energy that weakens could eventually reverse, allowing gravity to reassert itself, potentially leading to a new collapse, a new Big Bang, a cyclical universe that has happened before and will happen again. The DESI results, if they hold, suggest that dark energy is weakening. The universe may not be accelerating forever. The cold, dark endpoint of lambda CDM may not be our destiny after all, or it might be. The data are not yet conclusive. The models are not yet settled. The future of the cosmos remains, as it has always been, stubbornly uncertain. What we can say is this: something very strange is happening in the data. The most comprehensive survey of cosmic expansion ever undertaken is returning results that do not fit the standard model. The 25-year reign of lambda CDM may be coming to an end, and the physics that replaces it, whatever it turns out to be, will reshape our understanding of what the universe is and what it will become. The campfires of civilization, burning on this small rocky planet, are surrounded by a darkness that we have never truly understood. We gave that darkness a name. We called it dark energy. We wrote equations for it, measured it, claimed to comprehend it, and now the darkness is revealing that it is more complicated than we imagined. The next part of this story takes us deeper into the mathematics, into the theoretical models that could explain what DESI has found, into the history of our attempts to understand what empty space really contains. We will meet the scientists who first proposed quintessence, follow the debates that have raged for decades about the nature of the vacuum, and confront the unsettling possibility that our best theories of physics are fundamentally incomplete. But first, let this settle. Let the scale of what is at stake sink in. The universe is expanding. That expansion is accelerating. The force driving that acceleration appears to be changing over time, and if it is, then the standard model of cosmology, the framework that has explained more observations with more precision than any cosmological theory in history, is wrong. Not wrong about details, not wrong about parameters, wrong about the nature of reality itself. The vacuum of space is not what we thought it was. And that brings us to the question that has haunted theoretical physics for nearly 3 decades. If the cosmological constant is not the answer, what is? To understand the alternatives, we need to go back. Back to the moment when physicists first realized that empty space might not be empty at all. Back to the strange and counterintuitive discoveries that forced them to confront a vacuum that was far more complicated than anyone had imagined. Back to the birth of an idea called quintessence. The name itself is ancient. Aristotle used it to describe the fifth element, the substance that made up the heavens, the ethereal material from which the stars and planets were formed. Earth, water, air, fire. These were the 4 elements of the terrestrial world, the stuff of change and decay. But the heavens were eternal, perfect, unchanging. They required something else, something purer. Aristotle called it ether, or the 5th essence, quintessence. 24 centuries later, physicists borrowed that name for something completely different. In 1998, the same year that the supernova observations revealed the accelerating expansion of the universe, 2 theoretical physicists, Robert Caldwell at Dartmouth and Rahul Dev and Paul Steinhardt at the University of Pennsylvania, proposed a radical alternative to the cosmological constant. What if, they asked, dark energy is not a constant at all? What if it is a field? This is a word that requires some unpacking. In physics, a field is not a meadow or a playing surface. It is something more abstract and more fundamental. A field is a quantity that has a value at every point in space and time. The temperature in a room is a field. At every location there is a temperature. The electric field around a charged particle is a field. At every point there is a strength and a direction. Gravity itself, in Einstein's general relativity, is described by a field, the curvature of space-time at every location in the universe. Fields are not just useful mathematical tools. In the quantum world, they are the fundamental building blocks of reality. Every particle you have ever heard of, electrons, quarks, photons, the Higgs boson, is not really a tiny ball of matter bouncing through space. It is an excitation of a field. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field. The Higgs boson is a ripple in the Higgs field. All of matter and all of force at its deepest level is fields and their interactions. Caldwell, Dave and Steinhardt proposed that dark energy might be another such field. Not the cosmological constant, which is fixed and unchanging, but a new field that permeates all of space and whose energy drives the expansion of the universe. They called it quintessence, after Aristotle's 5th element, and unlike the cosmological constant, quintessence could change. The idea was elegant in its simplicity. Imagine a ball rolling down a hill. At any given moment, the ball has a certain amount of potential energy, determined by its height above the bottom. As the ball rolls, its height changes, and so does its potential energy. Now imagine that the hill is not made of rock or earth, but of space-time itself, and the ball is not a ball but the value of a field at every point in the universe. The shape of the hill, what physicists call the potential, determines how the field evolves over time. A steep potential means the field changes quickly. A flat potential means it changes slowly. And the height of the field on that potential, at any given moment, determines how much energy it contributes to the universe. This is quintessence. A field rolling down a potential, slowly changing its value over cosmic time, contributing an energy density to the universe that changes as it rolls. If the potential is almost flat, the field changes very slowly, and quintessence looks almost exactly like a cosmological constant. The energy density stays nearly constant. The expansion accelerates. Lambda CDM appears to work, but the key word is almost. If you look closely enough, if you measure precisely enough, you might be able to detect the subtle difference between a true constant and a slowly rolling field. The energy density of quintessence would not be exactly the same at redshift 2 as it is at redshift 0. The equation of state parameter, W, would not be exactly -1. It would be slightly different, and that difference would evolve over time. This is precisely what the DESI results suggest. The data show changing. The data show dark energy behaving like something that is not a constant. Stop and feel the weight of that. For a quarter century, cosmologists have debated whether quintessence is real or whether it is just a theoretical curiosity, a mathematical possibility with no evidence to support it. The cosmological constant was simpler. It required no new physics, no new fields, no new parameters. Occam's razor favoured lambda. The data for 25 years were consistent with lambda, and now, for the first time, the data are pointing somewhere else. But quintessence is not the only possibility. It is in some ways the most conservative alternative to the cosmological constant. There are other models, stranger models that challenge our understanding of physics at an even deeper level. To see why, we need to confront one of the most embarrassing problems in all of theoretical physics. It is called the cosmological constant problem, and it has been described as the worst prediction in the history of science. Here is the problem in its starkest form. According to quantum field theory, the vacuum of space is not empty. It is seething with activity, filled with virtual particles that pop in and out of existence on timescales so short that they never become real. These virtual particles are not a metaphor or a mathematical trick. They are a direct consequence of the uncertainty principle, one of the foundational pillars of quantum mechanics. You cannot have a field that is perfectly still, with zero energy, at any point in space. The uncertainty principle forbids it, so even the emptiest possible space, the vacuum, must have some minimum level of activity, some minimum energy. Physicists call this the vacuum energy. Now here is the problem. When you add up all the contributions to the vacuum energy from all the quantum fields we know about, the electron field, the quark fields, the photon field, the Higgs field, and all the rest, you get a number. And that number is absurdly, catastrophically, almost inconceivably large. Let me try to convey the scale of the mismatch. The observed dark energy density, the amount of energy per cubic meter of space that is driving the accelerating expansion of the universe, is about 0.6 × 10⁹ joules per cubic meter. Written out, that is about 0.006 joules in every cubic meter of the cosmos, a small number, an almost negligible amount of energy. The vacuum energy predicted by quantum field theory, using the most straightforward calculation, is about 10⁻113 joules per cubic meter. That is a 1 followed by 113 zeros. The ratio of the predicted value to the observed value is 10⁻122, a 1 followed by 122 zeros. This is not a factor of 2 or a factor of 10. This is a discrepancy so vast that there are not enough atoms in the observable universe to count it. If you predicted the weight of a single grain of sand and got something heavier than 1 billion universes, you would have made a more accurate prediction than quantum field theory makes for the vacuum energy. This is the cosmological constant problem. Our best theory of particle physics predicts a vacuum energy that is 122 times larger than what we observe, and yet the universe exists. Galaxies form, stars burn, life evolves. Somehow the actual vacuum energy is nearly, but not exactly, zero. For decades, physicists have struggled with this problem. There are essentially three possible responses. The first is that there is some unknown mechanism that cancels the vacuum energy almost perfectly, reducing it from its enormous predicted value to the tiny observed value. But nobody has ever found such a mechanism. Every proposal has failed. The problem stubbornly resists solution. The second is that our calculation is wrong. Perhaps the straightforward approach to adding up vacuum contributions is missing something fundamental. Perhaps quantum field theory itself breaks down at high energies, and the huge predicted value is an artifact of a theory being pushed beyond its domain of validity. This is possible, but it requires new physics that we do not yet understand. The third is the anthropic argument. Perhaps the vacuum energy varies from place to place in a vast multiverse, taking different values in different regions. In most regions, the vacuum energy is enormous, and the universe either collapses immediately or expands so fast that no structure can form. Only in rare regions where the vacuum energy happens to be small can galaxies form, stars ignite, and observers evolve to ask questions about dark energy. We live in one of those rare regions, not because there is anything special about our universe, but because we could not exist anywhere else. This is the controversial landscape picture associated with string theory and the idea of eternal inflation. It has ardent defenders and bitter critics. Some physicists see it as a profound insight into the nature of reality. Others see it as a surrender, an admission that we cannot calculate the vacuum energy and must instead invoke selection effects. The debate has raged for over 2 decades, and it remains unresolved. But here is what matters for our story. If the cosmological constant is just that, a constant fixed and unchanging, then some form of fine-tuning or anthropic selection seems almost unavoidable. The vacuum energy needs to be nearly perfectly cancelled by some mechanism we do not understand, and that cancellation needs to hold across all of cosmic time. But if dark energy is dynamic, if it is a field like quintessence that can evolve, then new possibilities open up. Perhaps the field is slowly rolling toward a value of 0. Perhaps the current dark energy density is not fine-tuned, but is instead a transient phase, a moment in cosmic history when the field happens to have a small but non-zero value. Perhaps the cosmological constant problem is not a permanent embarrassment, but a clue, pointing toward physics we have not yet discovered. The DESI results, if confirmed, would favour the dynamic picture. They would suggest that dark energy is not a constant that requires extraordinary explanation, but a field that is doing what fields do, changing. This is why the stakes are so high. This is why cosmologists around the world are scrutinising the data, checking the systematics, running new simulations, proposing new observations. The DESI results touch on one of the deepest problems in physics. They offer a potential path out of the cosmological constant problem, or they might be a mirage, a statistical fluctuation that will fade when more data arrive. Let us go deeper into the theoretical landscape. Quintessence is the simplest form of dynamic dark energy, but it is far from the only one. Over the past 25 years, theorists have proposed dozens of alternatives, each with its own predictions, its own signatures, its own implications. One class of models involves a dark energy field that interacts with dark matter. In the standard picture, dark energy and dark matter are independent. Dark matter clumps under gravity, forming the scaffolding for galaxies. Dark energy pervades all of space uniformly, driving the acceleration. But what if these two components are not independent? What if there is a coupling between them, an exchange of energy that causes one to affect the other? Such coupled dark energy models can produce signatures that look very different from a cosmological constant. The growth of structure, the way galaxies and clusters form over cosmic time, can be altered. The ratio of dark matter to dark energy can change in ways that a pure cosmological constant does not allow. Some of these models predict exactly the kind of evolving W parameter that DESI has observed. Another class of models modifies gravity itself. Einstein's general relativity is extraordinarily well tested in the solar system and in binary pulsars, but it has never been directly tested on cosmological scales. What if gravity behaves differently on the largest distances? What if there are corrections to Einstein's equations that become important only when you consider the expansion of the universe as a whole? These modified gravity models come in many varieties. Some add extra dimensions to space-time. Some promote the cosmological constant from a fixed number to a dynamic scalar field. Some introduce new gravitational degrees of freedom that alter how space expands. Almost all of them can, with the right choice of parameters, mimic the DESI results. The challenge is distinguishing between these possibilities. A measurement of the expansion history alone is not enough. You could have 100 different theoretical models, each with its own physical mechanism, each predicting the same expansion history, but different behaviours in other observables. To break the degeneracy, cosmologists need more than just the expansion rate. They need to measure the growth of structure, how fast galaxies cluster over time. They need to measure the distribution of matter on large scales, looking for subtle imprints of modified gravity or dark sector interactions. They need to cross-check the results from baryon acoustic oscillations with other probes, gravitational lensing, galaxy clustering, the cosmic microwave background, the abundance of galaxy clusters. This is what makes the DESI results so tantalizing and so frustrating at the same time. The data are suggestive. The hint of evolving dark energy is there, stronger than any previous survey has seen. But the error bars are still large enough to accommodate the cosmological constant. The tension is at the 2 to 3 sigma level, which in particle physics would barely raise an eyebrow. New physics claims require 5 sigma, a threshold that corresponds to a 1 in 3.5 million chance of a statistical fluke. DESI is nowhere near that threshold yet, and yet the consistency is striking. When DESI combines its data with the cosmic microwave background measurements from the Planck satellite, and with supernova observations from other surveys, the preference for evolving dark energy grows stronger. Different data sets, measuring different things, probing different epochs of cosmic history, are all pointing in the same direction. That coherence is harder to explain as a statistical accident. There is another piece of the puzzle that we have not yet examined. It involves a tension that has been simmering in cosmology for nearly a decade, a disagreement between different measurements that has refused to go away. It is called the Hubble tension, and it may be connected to what DESI has found. The Hubble constant is the rate at which the universe is expanding today. It is one of the most fundamental numbers in cosmology, the conversion factor between distance and recession velocity, the heartbeat of cosmic expansion. Measuring it accurately has been a goal of astronomers for nearly a century. There are 2 basic ways to measure the Hubble constant. The first is the distance ladder method. You start with objects whose distances you can determine directly, stars whose parallax you can measure, for instance. Then you use those calibrated distances to determine the brightness of standard candles like Cepheid variable stars. Then you use those Cepheids to calibrate the brightness of Type Ia supernovae in nearby galaxies. Then you use those supernovae to measure the expansion rate out to cosmological distances. Each rung of the ladder builds on the previous one, extending your reach further into the universe. The second method uses the cosmic microwave background. The CMB encodes information about the early universe, including the size of the sound horizon at the time of recombination, the physical scale of those baryon acoustic oscillations we discussed earlier. By measuring the angular size of the sound horizon in the CMB, and combining it with a cosmological model, you can infer what the expansion rate must be today. This is an indirect measurement, dependent on the model, but it is extraordinarily precise. Here is the problem. The 2 methods give different answers. The distance ladder measurements, led by a team using the Hubble Space Telescope and headed by Nobel Laureate Adam Rees, find a Hubble constant of about 73 km per second per megaparsec. The CMB measurements from the Planck satellite, assuming the standard lambda CDM model, find a value of about 67 km per second per megaparsec. The difference is about 8%. This might not sound like much, but the uncertainties on both measurements are now so small that the discrepancy is statistically significant, above 5 sigma by some analyses. If both measurements are correct, then something is wrong with our model of the universe. For years, cosmologists have searched for systematic errors that could explain the tension. The distance ladder is notoriously difficult, with each rung introducing potential biases. The CMB analysis depends on assumptions about the composition and geometry of the universe. Perhaps one or both measurements are subtly wrong, but despite intensive effort, no convincing systematic error has been found. the tension persists, and increasingly cosmologists are entertaining the possibility that the tension is real, that it is telling us something about physics beyond the standard model. This is where dynamic dark energy enters the picture. If dark energy is not a constant but evolves over time, the relationship between the early universe and the late universe changes. The CMB measurement of the Hubble constant depends on extrapolating from the conditions at recombination to the present day using a cosmological model. If that model is wrong, if dark energy behaves differently than lambda CDM assumes, then the extrapolation gives the wrong answer. Some forms of dynamic dark energy can ease the Hubble tension. If dark energy was weaker in the past and has been growing stronger, the expansion history changes in a way that can bring the early universe and late universe measurements into closer agreement. The DESI results, intriguingly, show the opposite trend, dark energy weakening over time. This does not obviously solve the Hubble tension, but it does add another piece to the puzzle, another indication that something in the standard model is not quite right. There is a phrase that cosmologists use when discussing these anomalies. They call it the dark sector, encompassing both dark matter and dark energy, the parts of the universe we cannot see directly, the components that make up 95% of the total energy density, the vast majority of what exists. We have named the darkness, we have parameterized it, we have fitted into our models with remarkable precision, but we do not understand it. Picture what this means. You're sitting in a room, reading these words or listening to them, surrounded by walls and furniture and air. All of that, the atoms in the walls, the molecules of oxygen you breathe, the electromagnetic radiation that carries this information to your eyes or ears, constitutes less than 5% of the universe. The rest is dark matter, clumping invisibly around galaxies, and dark energy, filling the space between them. You're embedded in a cosmos where most of what exists is fundamentally unknown to you. The lambda CDM model has been our best attempt to parameterize that ignorance. It gives dark matter and dark energy simple mathematical forms, dark matter that clusters, dark energy that remains constant, and shows that those simple forms can explain an enormous range of observations. But the model does not tell us what dark matter is made of. It does not tell us what dark energy is. It does not explain why the vacuum energy is so much smaller than quantum field theory predicts. It does not resolve the Hubble tension. It is a description, not an explanation. The DESI results suggest that the description may be incomplete. The cosmological constant, that simple fixed number, may need to be replaced by something richer. The vacuum is not static. The darkness is changing. Let that settle for a moment. 25 years ago, the accelerating expansion of the universe was discovered, and lambda returned from exile to become the cornerstone of modern cosmology. Now, for the first time, we have data suggesting that lambda is not the final answer. The field that drives the acceleration, whatever it is not frozen. It is rolling. It is evolving. It is alive, in the sense that fields in physics are alive, dynamic, changing, subject to laws we do not yet fully understand. The theoretical possibilities stretch out before us like a branching tree. Quintessence, coupled dark energy, modified gravity, extra dimensions, phantom energy. Each branch leads to a different future for the universe, a different answer to the question of cosmic fate. And we do not yet know which branch we are on. What we know is this. The instruments are getting better. The data are accumulating. DESI will continue observing for years, gathering spectra from millions more galaxies, pushing the error bars smaller and smaller. Other surveys, the Vera C. Rubin Observatory, the Euclid Satellite, the Nancy Grace Roman Space Telescope, will add their own measurements, probing different aspects of cosmic expansion and structure growth. The next decade will see an unprecedented flood of cosmological data. Somewhere in that flood of data lies the answer. The truth about dark energy is encoded in the light that has travelled billions of years to reach our telescopes, in the patterns of galaxy clustering, in the subtle distortions of gravitational lensing, in the faint glow of the cosmic microwave background. The universe has been keeping this secret since the beginning, and now, for the first time, we have the tools to uncover it. The instruments themselves are worth understanding, not because their technical specifications make for thrilling narrative, but because the precision they achieve is itself a kind of poetry, a human attempt to reach across billions of years and measure something that should be unmeasurable. The Dark Energy Spectroscopic Instrument sits atop Kitt Peak in southern Arizona, mounted on the 4-metre Mayall telescope. The telescope itself is not new. It was built in the 1970s, designed for a different era of astronomy, when the concept of dark energy had not yet been invented and the expansion of the universe was thought to be slowing down. But the instrument attached to it is something else entirely. DESI contains 5,000 fibre optic cables, each one thinner than a human hair, each capable of capturing light from a single galaxy or quasar. These fibres are not fixed in place. They are mounted on tiny robotic positioners, miniature actuators that can swivel and tilt with micrometer precision, aligning each fibre with a target object in the sky. In the time it takes to read this sentence, those 5,000 robots can reconfigure themselves into a new pattern, ready to collect light from a completely different set of cosmic targets. Picture the scale of this operation. On a single night of observing, DESI can measure the spectra of 100,000 galaxies. In a year, that adds up to tens of millions. Over its planned 5-year survey, the instrument will map the positions and recession velocities of over 40 million objects, creating the most detailed 3-dimensional picture of the universe ever assembled. Each spectrum tells a story. When the light from a distant galaxy enters one of those hair-thin fibres, it travels down the cable to a spectrograph, where it is split into its component wavelengths like sunlight passing through a prism. The resulting pattern, a rainbow with specific bright and dark lines, encodes information about the galaxy's chemical composition, its stellar populations, and crucially, its redshift. The redshift is the key. As light travels through an expanding universe, its wavelength gets stretched. The same phenomenon that shifts the pitch of an ambulance siren as it moves away from you shifts the colour of light from receding galaxies toward the red end of the spectrum. Measure the redshift, and you measure how fast the galaxy is moving away from us. Combine that with the galaxy's angular position in the sky, and you have a 3-dimensional coordinate, a location in the cosmic web. But here is where the precision becomes almost unbelievable. DESI does not simply measure redshifts as approximate values. It measures them with enough accuracy to detect the tiny imprint of acoustic oscillations, those sound waves frozen into the galaxy distribution, the standard ruler we discussed earlier. The characteristic scale of those oscillations corresponds to about 500 million light-years in the present-day universe. To use that ruler to measure the expansion history, you need to determine galaxy positions with corresponding precision. Think about what that means. You are measuring the distance to an object billions of light-years away, with enough accuracy to detect a pattern that spans 500 million light-years. It is like standing in New York and determining the distance to Los Angeles by measuring the spacing between mile markers along a highway you cannot see, using only the faint glow of headlights from cars driving along it. The statistics required to extract that signal are formidable. A single galaxy tells you almost nothing. Its position in the cosmic web is influenced by local gravitational effects, random motions, and observational uncertainties. But with millions of galaxies, the noise begins to average out, and the underlying pattern emerges. The baryon acoustic oscillations become visible not in any individual galaxy, but in the statistical correlations between galaxy positions, a slight excess probability of finding two galaxies separated by exactly that characteristic distance. This is big data cosmology, not the philosophical contemplation of individual objects, but the statistical machinery of pattern recognition applied to millions of data points. The universe becomes a dataset, and the dataset contains encoded within it the parameters of the model, including the equation of state of dark energy. Let me try to give you a feel for the statistical challenge. Imagine you're trying to measure a faint signal buried in noise. The signal has an amplitude of, say, 1%. The noise is much larger, fluctuations of 10 or 20%. If you have a single measurement, you cannot distinguish signal from noise. But if you have 1,000,000 measurements and you know the noise is random, the noise will average to 0 while the signal will add up. With 1,000,000 measurements, you can detect a signal that is 1,000 times weaker than the noise in any individual measurement. That is how baryon acoustic oscillation measurements work. Each galaxy pair is a noisy realization of an underlying probability distribution. The Bayo signal is a tiny bump in that distribution, a few percent excess probability at the characteristic distance. With enough galaxy pairs, that bump becomes statistically significant, and you can measure the expansion history. DESI has now analysed the first year of its survey data, roughly 6 million galaxies and quasars, 14 billion galaxy pairs. From those pairs, the collaboration extracted BAO signals at 7 different redshift bins, spanning from redshift 0.1 to redshift 4.2, a range that covers the past 12 billion years of cosmic history. The results, published in April 2024, caused the cosmological equivalent of an earthquake. For years, astronomers had measured dark energy using BAO and other techniques, and the results had been consistent with a cosmological constant, lambda, a fixed number, the vacuum energy that Einstein introduced in 1917, brought back from the dead in 1998, and enshrined in the Standard Model ever since. Measurement after measurement had found the equation of state parameter W to be indistinguishable from -1. But DESI found something different. When the collaboration fit their data using a model that allows W to change over time, letting dark energy evolve rather than remain constant, the fit improved. Significantly, the data preferred a universe where dark energy was stronger in the past and has been weakening over the billions of years since. The statistical significance is not overwhelming. In the language of particle physics, the preference for evolving dark energy is between 2 and 3 sigma, a 1 in 100 to 1 in 300 chance of being a statistical fluke. That is enough to be interesting, enough to be published in the most prestigious journals, enough to make headlines. But it is not enough to claim discovery. The history of physics is littered with 2 sigma anomalies that evaporated with more data. Fluctuations happen. Statistical noise can occasionally mimic a signal. Scientists have learned, through painful experience, to be cautious about results that fall short of 5 sigma, the threshold traditionally required to claim a discovery in particle physics. But there is a critical difference between DESI and a typical anomaly. The DESI result does not come from a single measurement. It comes from combining BAO data at 7 different redshift bins with external datasets, measurements of the cosmic microwave background from the Planck satellite, observations of type Ia supernovae. When those datasets are analysed together, the preference for evolving dark energy becomes stronger, and there is something else. The direction of the departure from lambda CDM is not arbitrary. The data suggest a specific pattern. Dark energy was stronger in the past and has been getting weaker over time. This is precisely what certain theoretical models predict. Quintessence, the rolling scalar field, generically produces this behaviour. The field starts high on its potential energy curve, the vacuum energy is large, and as the field rolls downhill, the energy decreases. The universe, in other words, is not just telling us that lambda CDM is wrong. It may be telling us what the replacement looks like. Stop and feel the weight of that. For a quarter century, the cosmological constant has been the framework within which we understand the accelerating expansion. It has been taught in textbooks, built into simulation codes, assumed in analyses of galaxy evolution and structure formation. The entire edifice of modern cosmology rests on the assumption that dark energy is a fixed constant. If DESI is right, that assumption is wrong. Not slightly wrong. Fundamentally wrong. The vacuum is not a passive backdrop with a fixed energy density. It is a dynamic medium, changing over cosmic time, its properties evolving as the universe ages. The implications cascade through every branch of cosmology. The age of the universe would need to be recalculated. The distance scale to faraway objects would shift. The predicted clustering of galaxies at different epochs would change. The forecast for the ultimate fate of the cosmos would become uncertain again. And there is a deeper implication still. If dark energy is not a cosmological constant, if it is instead a rolling scalar field, then that field is something. It is a new component of nature, as fundamental as electromagnetism or gravity. Finding it would be the discovery of a fifth force, or at least a fifth fundamental field, something beyond the standard model of particle physics and beyond the standard model of cosmology. That is not a small thing. But let us be careful. Let us be precise about what the DESI collaboration actually measured and what they actually claimed. The paper published in April 2024 presents the BAO measurements from the first year of DESI data. Those measurements, analysed using a model called W0A, show a preference for evolving dark energy at the 2 to 3 sigma level. But the paper also presents results using the simpler lambda CDM model, and those results are perfectly consistent with previous measurements. Lambda CDM fits the DESI data adequately. It just does not fit it optimally when compared to more flexible models. This distinction matters. The data do not rule out lambda CDM. They do not prove that dark energy is evolving. What they show is that if you allow dark energy to evolve, the fit improves, and the best fit parameters point in a specific direction towards stronger dark energy in the past. The technical term for this situation is model selection. When you have two models, one simple, one complex, and the complex model fits the data slightly better, you face a question. Is the improvement in fit worth the added complexity? There are statistical tools to address this question, penalizing complex models for their extra parameters. By those measures, the evidence for evolving dark energy is suggestive, but not definitive. Science proceeds through exactly this kind of careful inference. Results like DESI are not the end of the story. They are the beginning of a new chapter, a signal that something may be wrong with the standard picture, a target for future observations to confirm or refute. The DESI collaboration knows this. Their paper explicitly states that the results are intriguing but not conclusive. More data are needed. The full 5-year DESI survey will triple the number of galaxies and reduce the statistical uncertainties significantly. If the preference for evolving dark energy persists and strengthens with more data, the case will become compelling. If it fades, we will conclude it was a fluctuation. Meanwhile, other experiments will provide independent tests. The Vera C. Rubin Observatory, under construction in Chile, will begin its legacy survey of space and time in 2025. This survey will map billions of galaxies and measure their shapes with exquisite precision, enabling a technique called weak gravitational lensing, using the distortion of background galaxy images by foreground mass to map the distribution of dark matter and constrain dark energy. The Euclid satellite, launched by the European Space Agency in 2023, is already collecting data. From its vantage point in space, free from the blurring effects of Earth's atmosphere, Euclid will measure galaxy shapes and redshifts across a third of the sky, providing another independent probe of cosmic acceleration. And the Nancy Grace Roman Space Telescope, scheduled for launch in 2026, will combine infrared imaging with spectroscopy to measure both BAO and supernova distances, cross-checking the results from DESI and Euclid. The next decade will be the decade of dark energy. Every major observatory, ground-based and space-based, is being marshalled for this single question. Is dark energy a cosmological constant, or is it something else? Let me try to explain why this question matters so much, not just to cosmologists, but to anyone who has ever looked up at the night sky and wondered what it all means. If dark energy is a cosmological constant, the universe has a fixed destiny. The expansion will continue to accelerate. The galaxies beyond our local group will recede beyond the cosmic horizon, and in the far future, our descendants, if there are any, will find themselves in an island universe, surrounded by empty space with no evidence that other galaxies ever existed. But if dark energy is evolving, that destiny becomes uncertain. The field could continue to weaken, and the acceleration could slow down or even reverse. The field could stabilize at a new value, leading to a different long-term expansion rate. Or, and this is the possibility that haunts some physicists, the field could evolve in the other direction, strengthening over time, leading to a catastrophic event called the Big Rip, in which the expansion becomes so violent that it tears apart galaxies, stars, planets, atoms, and eventually space-time itself. The DESI results, interpreted naively, point toward weakening dark energy. The vacuum is losing its punch, but extrapolating from present trends to the far future is always risky. The field could have complex dynamics that we do not yet understand. What we can say is this: the question of cosmic fate, which seemed settled for a generation, is suddenly open again. And there is an even deeper question lurking beneath the data. Why is there dark energy at all? The existence of the cosmological constant was always philosophically troubling. The measured value is so small, 120 orders of magnitude smaller than quantum field theory predicts, that it seems to require an almost miraculous cancellation between different contributions to the vacuum energy. This is the cosmological constant problem, arguably the worst fine-tuning problem in all of physics. If dark energy is a rolling scalar field instead of a true cosmological constant, the problem changes character but does not disappear. Now you have to explain the potential energy function of the field, why it has the shape it has, why the field started in a particular location on that potential, why it has evolved in the way it has. The fine-tuning may be relocated rather than eliminated, but there is a tantalizing possibility. Some quintessence models include mechanisms that drive the field toward configurations where the effective cosmological constant is small. These are called tracking solutions, and they offer a glimmer of hope that the smallness of dark energy might be explained dynamically rather than imposed by hand. The DESI data, if confirmed, would tell us that we are not living with a bare cosmological constant. We are living in a universe permeated by a dynamic field with a specific potential energy function. Determining that function, mapping out its shape from observational data, would be one of the great achievements of 21st century physics. We are not there yet. The error bars are too large, the systematic uncertainty is too incompletely understood, the alternative models too numerous, but the path is becoming visible. Picture what the next few years will bring. DESI will continue observing, adding millions more galaxies to its catalogue. Euclid and Rubin will provide complementary data, constraining dark energy from different angles. The statistical uncertainties will shrink. The systematic effects will be better controlled. Either the hint of evolving dark energy will solidify into a detection, or it will fade into the noise. Either outcome will be scientifically important. If lambda CDM survives, it will have passed another stringent test, and the cosmological constant will be even more firmly established as the correct description of dark energy. If lambda CDM fails, a new era of cosmology will begin, one in which we must grapple with a richer and stranger universe than we had imagined. The darkness is changing, or perhaps it is not. The data will decide, and somewhere in the patterns of galaxy light arriving at our telescopes, encoded in correlations we have barely begun to unravel, the answer is waiting. But before we can trust that answer, we need to understand where the DESI result fits in a broader landscape of cosmological puzzles. The hint of evolving dark energy does not exist in isolation. It arrives at a moment when the standard model is already under pressure, when cracks have been appearing from other directions. One of those cracks has a name: the Hubble tension. The Hubble tension is one of those problems that sounds technical until you realize what it actually means. Two different methods of measuring how fast the universe is expanding give two different answers. And they should not. They should agree. The universe has one expansion rate, not two. If our measurements are correct and our theory is correct, every method of determining that rate should converge on the same number. They do not. Let me tell you what the Hubble constant is, because the name carries more history than most scientific terms. In 1929, Edwin Hubble published a paper demonstrating that galaxies are moving away from us, and that the more distant a galaxy is, the faster it recedes. This relationship, velocity proportional to distance, was the first observational evidence that the universe is expanding. The constant of proportionality, the number that tells you how many kilometers per second faster a galaxy recedes for every megaparsec of additional distance, became known as the Hubble constant. Today we call it h0, or h0, and measuring it precisely has been one of the great obsessions of modern cosmology. The reason it matters is that h0 tells you the age and size of the universe. If the expansion is faster, the universe is younger, because everything was closer together more recently. If the expansion is slower, the universe is older. The Hubble constant is not just a number describing current conditions. It is a key that unlocks the entire history of cosmic expansion. Get it wrong, and everything downstream, in the age of the oldest stars, the distances to far galaxies, the time available for cosmic structure to form, becomes suspect. For decades, measuring h0 was notoriously difficult. Different techniques gave wildly different results, sometimes varying by a factor of 2. But by the early 2000s, the measurements seemed to be converging. The best value, determined by the Hubble Space Telescope's key project, was around 72 kilometers per second per megaparsec. This meant that for every megaparsec of distance, about 3.26 million light-years, a galaxy's recession velocity increases by 72 kilometers per second. The universe seemed to have a well-determined expansion rate, and the remaining debates were about the second decimal place. Then two things happened. The first was the Planck satellite. Launched in 2009 by the European Space Agency, Planck measured the cosmic microwave background, the ancient light from the baby universe, with unprecedented precision. The CMB contains tiny temperature fluctuations, hot spots and cold spots, that encode information about the conditions in the early universe. by analysing the statistics of those fluctuations, their angular sizes, their relative amplitudes at different scales. Cosmologists can extract the fundamental parameters of lambda CDM, including the Hubble constant. But here is the crucial point. The Hubble constant that Planck measures is not a direct observation of the current expansion rate. It is an inference. Planck sees the universe as it was 380,000 years after the Big Bang. To get from those ancient conditions to a present-day expansion rate, you have to assume a cosmological model. You have to tell the computer what the universe is made of, how it has evolved, how dark energy and dark matter and ordinary matter have interacted over 13.8 billion years. Only then can you calculate what h0 should be today. For the standard lambda CDM model, Planck's data gives a Hubble constant of about 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. The second thing that happened was that the local measurements got better. By local, I mean measurements that do not rely on the early universe or on cosmological models. Instead, you build what astronomers call a distance ladder. You start with objects whose distances you know independently. Cepheid variable stars in our own galaxy, for instance, whose intrinsic brightness can be calculated from the period of their pulsations. You use those to calibrate the brightness of Type Ia supernovae in nearby galaxies. Then you observe Type Ia supernovae in more distant galaxies and use them to measure how fast those galaxies are receding. The ratio of recession velocity to distance gives you h0 directly, without assuming anything about cosmology. The distance ladder measurements improved dramatically over the 2010s, thanks largely to the work of Adam Rees at Johns Hopkins University and the SCHEERS collaboration. Their results consistently pointed to a Hubble constant around 73 to 74 kilometers per second per megaparsec, and the uncertainties kept shrinking. By 2019, the disagreement between the Planck value and the SCHEERS value had grown to more than 4 sigma, meaning the probability that the difference was just a statistical fluke was less than 1 in 15,000. Stop and feel the weight of that. Two of the most precise measurements in all of cosmology, using completely different methods, disagree by about 9%. One says the universe is expanding at 67 kilometers per second per megaparsec. The other says 73. They cannot both be right. Either one of the measurements is systematically wrong, or the standard cosmological model is missing something. The immediate suspicion, of course, is that something is wrong with the measurements. Systematics are the bane of precision cosmology. Maybe the Cepheid calibration has errors. Maybe the Type Ia supernovae are not as standard as we think. Maybe Planck has some subtle instrumental effect we have not accounted for. This has been the focus of intense scrutiny for years. Independent teams have cross-checked the Cepheid results using alternative distance indicators. The TRGB method, tip of the red giant branch, provides an independent calibration of supernova distances and gives results similar to, though slightly lower than, the SCHEERS value. Gravitational lensing of distant quasars offers yet another path to h0, and it too tends to favour the higher local value. Meanwhile, the Planck analysis has been rechecked, reanalysed, and validated by independent groups using different statistical techniques. No smoking gun has emerged. The Planck systematics, as far as anyone can tell, are under control, which leaves the unsettling possibility that neither measurement is wrong, that the tension is real, and if the tension is real, it means lambda CDM is missing something. Some new physics is operating that changes either the early universe or the late universe in a way that our standard model does not capture. And this is where the DESI result becomes interesting. If dark energy is evolving, if it was stronger in the past and is weakening now, that changes the expansion history of the universe. It changes the relationship between the early universe, as seen by Planck, and the present universe, as measured by the distance ladder. Evolving dark energy could, in principle, help resolve the Hubble tension. Let me explain how. The Planck measurement of h0 is an inference based on the assumption that dark energy has been a cosmological constant throughout the universe's history. Under that assumption, the computer calculates forward from the early universe to today and arrives at 67.4 kilometers per second per megaparsec. But if dark energy was actually stronger in the past, if the universe was accelerating more rapidly in earlier epochs than lambda CDM predicts, then the inferred Hubble constant would shift. The early universe would have evolved into the present universe in a way that implies a faster current expansion rate. When cosmologists fit the DESI data together with other data sets, allowing for evolving dark energy, they find tantalizing hints that the Hubble tension might ease. The inferred value of H0 creeps up from 67 towards 70 or so. The gap between early universe and late universe measurements shrinks. Not all the way to zero, not yet, but enough to suggest that dynamical dark energy might be part of the solution. I need to be careful here. The DESI data by itself does not resolve the Hubble tension. The shift in inferred H0 is modest. Other proposed solutions, early dark energy, modified gravity, new neutrino physics, remain in play. And some analyses find that evolving dark energy actually makes certain tensions worse while easing others. The picture is messy. The error bars overlap. The conclusions depend on which datasets you combine and which priors you assume. But here is why this matters. For years, the Hubble tension existed as an isolated anomaly, a measurement disagreement, annoying but perhaps attributable to some subtle systematic we would eventually find. The DESI result changes that context. Now we have two separate lines of evidence pointing in the same direction, pointing towards something beyond lambda CDM. The Bayo data suggests W is greater than -1, evolving through the phantom divide. The Hubble tension suggests the Standard Model's expansion history is incomplete. These are different symptoms, but they might have the same disease. Cosmologists have a term for this kind of situation. They call it model stress. When your standard model is under stress from multiple directions, it becomes harder to attribute all the problems to measurement errors. The probability that several independent measurements are all wrong in exactly the way needed to produce coherent-looking anomalies is much lower than the probability that one measurement is wrong. The Hubble tension plus the DESI hint plus certain other oddities in the cosmic microwave background plus the growth rate discrepancy. When you stack these together, the stress on lambda CDM starts to look like strain, like the first signs of failure in a load-bearing structure. I mentioned the growth rate discrepancy just now, so let me unpack that briefly. In lambda CDM, the same equations that predict the expansion history also predict how fast cosmic structure grows. Dark matter clumps together under gravity, and the rate of that clumping depends on the amount of dark matter, the amount of dark energy, and the expansion rate. If you measure the cosmic microwave background, you can predict what the universe should look like today, how clustered the galaxies should be, how strong the gravitational lensing should be. The parameter that captures this is called S8, and it combines information about the matter density and the amplitude of density fluctuations. What astronomers have found over the past several years is that direct measurements of cosmic structure today seem to show slightly less clumping than lambda CDM predicts. The S8 tension, as it is called, is not as severe as the Hubble tension. The disagreement is around 2 to 3 sigma, depending on which measurements you use, but it points in the same direction. The late universe is slightly different from what we would expect by evolving the early universe forward under the standard assumptions. Again, evolving dark energy could play a role. If dark energy was stronger in the past, it would have slowed down the growth of structure, because accelerating expansion counteracts gravitational collapse. The universe would have had less time, in an effective sense, to build up the clumps of dark matter that we see today. The S8 tension might be telling us the same story as the Hubble tension and the DESI BAO data, or it might not. This is the frustrating reality of precision cosmology in 2024. We have multiple hints, multiple anomalies, multiple tensions. They point in vaguely compatible directions, but none of them is individually conclusive. Each one could be explained away as a systematic error, as a statistical fluctuation, as an artifact of analysis choices. The case for new physics is not proven. It is circumstantial. A preponderance of evidence, perhaps, but not beyond reasonable doubt. And yet. Think about what it would mean if all these hints turn out to be real, if the universe is not described by lambda CDM but by something richer. Not a universe with a cosmological constant, but a universe with a scalar field pervading all of space, a field with its own dynamics, its own potential energy landscape, its own trajectory through configuration space. Not a universe where dark energy is a brute fact, but one where dark energy has a history, a present, and a future that differ from each other. Not a universe where the fundamental constants are truly constant, but one where the effective equation of state evolves over billions of years. The implications ripple outward in every direction. Our understanding of the early universe would need revision. Our predictions for the far future would become uncertain. The standard model of particle physics, already incomplete because it does not incorporate gravity or dark matter, would face new challenges. What is this scalar field? How does it interact with ordinary matter, if at all? Is it related to the Higgs field, which also pervades all of space? Is it connected to inflation, the hypothesized period of exponential expansion in the first fraction of a second? Is it part of a larger theory we have not yet discovered, some framework that unifies gravity and quantum mechanics and explains why the laws of physics take the form they do? These questions feel premature. The data is not strong enough to support this weight of speculation, but scientists do not work only on proven facts. They work on promising hints. They build instruments and design surveys based on what the data might become, not just what it currently shows. The next generation of cosmological observations, the full DESI dataset, the Euclid satellite, the Vera Rubin Observatory, CMB-S4, these are designed precisely to resolve questions like these. Within 5 to 10 years, we will know whether the DESI anomaly is real or a mirage. Let me tell you about the people who will make that determination. They are not, for the most part, household names. They do not appear on talk shows or win popular science awards. They are graduate students and postdocs and mid-career researchers, spending their nights at telescopes or their days writing code to analyze spectra. They argue about calibration techniques at conferences. They debate statistical methods in paper comment sections. They worry about selection effects and fiber collisions and atmospheric seeing. Their work is painstaking, incremental, often frustrating. Most of their effort goes into quantifying uncertainties, not discovering new truths. But this is how science works at the frontier. The big discoveries do not arrive with trumpets. They arrive as anomalies, small deviations from expectation, patterns that should not be there, numbers that do not quite match. Anomalies are almost always wrong. Almost always, when you look more carefully, the deviation disappears. A systematic you had not considered, a bug in the code, a statistical fluctuation that seemed significant only because you looked at so many things. Sometimes, though, the anomaly survives. You check everything, and it is still there. Other people check it with different methods, and they find it too. The deviation grows more significant as more data arrives. The systematic effects are ruled out one by one. The statistical fluctuation becomes less and less probable, and eventually what started as a hint becomes a discovery. We do not know yet whether DESI is showing us something real. The collaboration is careful to emphasize the uncertainties. The cosmologists who analyze the data are professionally skeptical, trained to resist the seduction of exciting results. They know how many anomalies have faded into noise over the years. They know the history of faster-than-light neutrinos and cold fusion claims, and all the other signals that seemed revolutionary until they were not. But they also know that some anomalies are real, that the cosmic microwave background was once an anomaly, that dark energy itself was once an anomaly, a strange acceleration in the supernova data that no one expected. That progress in physics often comes from exactly this kind of tension between theory and observation. The darkness that fills our universe may be changing its nature while we watch, or it may be exactly what we thought, a cosmological constant, static and eternal, Einstein's greatest blunder transformed into his most prescient insight. The measurements will tell us. The baryonic acoustic oscillations will speak if we can learn to hear them clearly. The correlations in the galaxy distribution, encoded over billions of years, carry the answer. We are listening. The question is whether we are listening carefully enough, with instruments precise enough, with models flexible enough, to recognize the truth when it emerges from the data. And there is something else the DESI collaboration has been grappling with, something that makes the interpretation even more complicated. The measurements do not just hint at evolving dark energy, they hint at a specific kind of evolution, one where the dark energy density was higher in the past and has been decreasing. This corresponds to an equation of state that was less negative in the past, moving toward more negative values as the universe ages. In the language of scalar field models, this suggests a field that has been rolling down its potential, losing energy as it goes. Imagine a ball rolling slowly down a very gentle slope. The ball has both kinetic energy from its motion and potential energy from its height on the slope. As it descends, it converts potential energy into kinetic energy. For quintessence, the equivalent is that the field's potential energy, which acts like dark energy, decreases as the field value changes. But here is the peculiar thing. The DESI data hints that W may have crossed from values greater than -1 to values less than -1. It has crossed the phantom divide. And in simple quintessence models, this is forbidden. A single scalar field with a well-behaved potential energy function cannot cross W equals -1. The math simply does not allow it. So either the hint is wrong, which is entirely possible given the uncertainties, or we need something more exotic than vanilla quintessence. Something like a field with the wrong sign kinetic energy. Something like two fields interacting in complicated ways. Something like modified gravity that only looks like evolving dark energy when analysed with standard tools. The options become stranger the more seriously you take the data. This is the double-edged sword of precision measurement. When your instruments become sensitive enough, they reveal not just the truths you were looking for, but also the complications you did not anticipate. The DESI data is both a window and a puzzle. It shows us something unexpected, but what exactly it shows remains frustratingly unclear. Perhaps the universe is telling us that our theoretical frameworks are too simple, that dark energy is not one thing but several, that the smooth quintessence models taught in graduate courses capture only part of a richer reality. Or perhaps the universe is playing tricks, and the data is showing us statistical noise shaped by selection effects and uncontrolled systematics. In either case, the next few years will be decisive. More spectra will be gathered, more galaxies will be mapped. The redshift range will extend further into the past. The error bars will shrink, or they will not. The phantom crossing will solidify into a discovery, or it will dissolve into ordinary quintessence, or it will fade entirely back into lambda CDM. The universe does not care which outcome we prefer. It simply is what it is. Our task is to read its signals through the noise, to extract its secrets from the light of distant galaxies, to build a model that matches not what we hoped for, but what the data demands. That model may turn out to be lambda CDM, weathered but intact. Or it may be something we have not yet fully imagined. And so we arrive at the question that haunts the edges of every cosmologist's thinking. The question that makes the DESI results not merely interesting, but potentially devastating. What if lambda CDM is not just incomplete, but fundamentally broken? What if the scaffolding we have built our understanding upon cannot hold the weight of new data? What if the model we teach to every graduate student, the model written into textbooks and funding proposals and public lectures, turns out to be a beautiful approximation that breaks precisely where precision matters most? This is not an abstract worry. It is a concrete technical problem with measurable consequences. Lambda CDM is not just a description of dark energy. It is a complete accounting of the universe's contents and their evolution. It specifies 6 numbers, just 6, that together determine everything from the temperature of the cosmic microwave background to the distribution of galaxies to the age of the universe itself. These 6 numbers have been measured with extraordinary precision over the past 2 decades. They fit together with an elegance that physicists find almost suspicious. Change one, and you must change others to maintain consistency. The model is tightly constrained, which makes it powerful. But that same tightness makes it fragile. Consider what happens if dark energy truly evolves. The expansion history of the universe changes. Not by much, but by enough to ripple through every other measurement. The distance to the cosmic microwave background shifts. The angular scale of the first acoustic peak shifts. The growth rate of structure shifts. The age of the universe shifts. Every number we thought we knew becomes uncertain again, dependent on assumptions we can no longer make. The 6-parameter lambda CDM model becomes a 7-parameter model at minimum, perhaps an 8 or 9-parameter model, depending on how we parameterize the evolution. And with more parameters comes more freedom to fit the data, which sounds good until you realize that it also means less predictive power. A model that can fit anything predicts nothing. The elegance drains away. This is not merely an aesthetic concern. It cuts to the heart of what science is supposed to do. A scientific model earns its keep by making predictions that could be wrong, but turn out to be right. Lambda CDM has passed this test repeatedly. It predicted the precise pattern of fluctuations in the cosmic microwave background before we could measure them with sufficient precision. It predicted the baryon acoustic oscillation scale before we had enough galaxies mapped to see it clearly. It predicted the growth of cosmic structure in ways that matched what we observed. Every prediction that could have killed it instead confirmed it. That track record is why lambda CDM is the standard model, not because physicists are attached to it emotionally, but because it keeps being right. But now we have data that might be showing it is wrong, and if the data is showing what it appears to show, then something in the model's foundation is cracked. Either the cosmological constant is not constant, or our understanding of how structure forms is incomplete, or both. Either way, the tightly constrained 6-parameter framework loosens. The elegant machine develops play in its joints. Let me try to give you a feel for how unsettling this is to the people who work on it professionally. Imagine you are an architect who has spent 20 years designing buildings based on certain assumptions about how steel behaves under stress. Your buildings have all stood. Your calculations have all worked. You have confidence in your methods because reality has validated them over and over. Now imagine someone shows you evidence that steel does not behave quite the way you thought. Not dramatically different. Your buildings are not going to fall down tomorrow, but subtly different, in ways that might matter for the tallest structures, or the longest spans, or the most ambitious designs. Suddenly, every calculation you have ever done needs to be revisited. Every building you plan to build needs to be rethought. The ground under your professional life has shifted, not catastrophically, but unmistakably. That is approximately how the DESI results feel to cosmologists who have built their careers on lambda CDM. The model is not dead, it may yet survive. But its invincibility has been questioned in a way it has not been questioned before, by data that is difficult to dismiss. And the complications do not stop there. The DESI results interact with other tensions in the cosmological framework, tensions that have been simmering for years and may now be approaching a boil. The most famous of these tensions carries a name that sounds almost gentle. Cosmologists call it the Hubble tension. It refers to a disagreement about the expansion rate of the universe today, the Hubble constant, designated h0. This number tells you how fast galaxies are receding from us as a function of their distance. A higher Hubble constant means a faster expansion rate and a younger universe. A lower Hubble constant means slower expansion and an older universe. There are two main ways to measure the Hubble constant, and they give different answers. The first way is to build what astronomers call a distance ladder. You start with objects whose distances you can measure directly. Cepheid variable stars, for instance, whose brightness pulsates in a way that correlates with their intrinsic luminosity. You use those to calibrate the distances to nearby galaxies. Then you use those galaxies to calibrate the distances to type Ia supernovae, which are so bright they can be seen across billions of light years. Step by step, rung by rung, you extend your reach into the cosmos. At each step you measure both distance and recession velocity. The ratio gives you the Hubble constant. This method, refined over decades by teams led by astronomers like Adam Rees and Wendy Friedman, yields a value around 73 kilometers per second per megaparsec. A galaxy 1 megaparsec away, about 3.26 million light-years, is receding from us at 73 kilometers every second. A galaxy 2 megaparsecs away is receding at 146 kilometers per second, and so on. The second way to measure the Hubble constant does not involve the local universe at all. Instead, it starts from the cosmic microwave background, that faint afterglow of the Big Bang that permeates all of space. The microwave background carries within its patterns a record of conditions in the early universe, and those conditions can be extrapolated forward to predict what the Hubble constant should be today, assuming lambda CDM is correct. The Planck satellite, which mapped the microwave background with exquisite precision, yields a predicted value around 67 kilometers per second per megaparsec. Stop and consider what this means. Two independent methods, both carefully executed, both cross-checked against multiple data sources, disagree by about 8%. That might not sound like much, but given the precision of the measurements, the disagreement is highly statistically significant. It is not a margin of error overlap. It is a genuine conflict. The probability that both measurements are correct and consistent with lambda CDM is less than 1 in a million, depending on exactly how you do the statistics. For years, cosmologists hoped this tension would resolve itself. Perhaps there was an error in the distance ladder, some systematic bias in how Cepheid distances were measured. Perhaps there was an error in the Planck analysis, some subtle miscalibration or modelling assumption. Enormous effort has been poured into checking both sides. The tension has not gone away. If anything, it has hardened. The James Webb Space Telescope, with its unprecedented infrared vision, was recently turned toward nearby Cepheid variables to check the distance ladder with independent data. The result confirmed the higher value. The tension persists. Now, here is where the DESI results become potentially crucial. The Hubble tension might be telling us that lambda CDM is wrong, and if lambda CDM is wrong because dark energy evolves, that evolution could potentially resolve the tension. The early universe and the local universe are connected by the expansion history between them. Change the expansion history, and you change the relationship between early time predictions and late time measurements. In some evolving dark energy models, the Hubble tension shrinks or disappears entirely. The higher local measurement and the lower early universe prediction can be reconciled if dark energy was behaving differently at different epochs. The DESI hint, dark energy density higher in the past, decreasing over time, goes in a direction that might help. Though whether it helps enough, and whether the specific evolution suggested by the data is exactly the right evolution to resolve the tension, remains unclear. This is why the DESI results landed with such impact. They did not just challenge lambda CDM in isolation. They landed in a field already primed for disruption, already grappling with unexplained tensions, already sensing that something might be off with the standard picture. The results gave shape to suspicions that had been circulating for years. They converted vague unease into a specific testable possibility. But we must be careful here. The history of cosmology is littered with hints that did not survive closer examination. Anomalies that looked significant faded with more data. Tensions that seemed irreconcilable dissolved when systematic errors were discovered. The DESI results are compelling, but compelling is not the same as conclusive. Let me tell you about another tension, one that receives less public attention, but troubles theorists just as deeply. It concerns the growth of cosmic structure, how quickly the web of galaxies and clusters formed from the nearly uniform early universe. Lambda CDM makes precise predictions about this. The model specifies how much matter exists, how much dark energy exists, how they interact, and how gravity pulls matter together over time. Given these ingredients, you can calculate how clumpy the universe should be today, compared to how clumpy it was in the past. The calculation is not simple. It involves numerical simulations of billions of particles moving under their mutual gravitational attraction. But it is well understood. Observations of the local universe, particularly measurements of gravitational lensing and galaxy clustering, suggest that the universe may be slightly less clumpy than lambda CDM predicts. The matter is there, but it is not gathered into structures quite as strongly as the model expects. This discrepancy is sometimes called the S8 tension, after a parameter that quantifies the amplitude of matter clustering. Like the Hubble tension, the S8 tension could be a systematic error, or a statistical fluctuation, or a real signal of new physics. If real, it suggests that something is suppressing the growth of structure. Dark energy that was stronger in the past, exactly what the DESI data hints at, would do precisely that. A higher dark energy density in the past would have accelerated the expansion earlier, making it harder for gravity to pull matter together. The universe would end up slightly less clumpy than expected. Do you see the pattern emerging? Multiple independent lines of evidence, each with its own uncertainties and potential issues, are pointing in a similar direction. The Hubble tension, the S8 tension, the DESI hints at evolving dark energy. None is conclusive on its own, but together they form a circumstantial case that something is not quite right with the standard model. This is how paradigm shifts often begin in physics, not with a single dramatic discovery, but with an accumulation of small anomalies that refuse to go away. Each one can be explained individually. Taken together, they begin to exert collective pressure on the framework. Eventually, if the pressure is real and not illusory, the framework bends or breaks. We are not there yet. Lambda CDM is not broken. But it is being tested in ways it has never been tested before, by data of a quality we have never had before. The next decade will determine whether the anomalies are signals or noise, whether the hints are harbingers or artifacts. And there is a deeper issue lurking beneath all of this, one that the DESI results bring into sharper focus. It concerns the nature of scientific models themselves and the strange relationship between mathematical elegance and physical truth. Lambda CDM works. it works remarkably well. It has passed test after test for 25 years, but it contains an ingredient that no physicist can explain, a cosmological constant with a value that appears completely arbitrary, set to whatever number happens to fit the data. There is no theory that predicts this value from first principles. There is no mechanism that explains why the cosmological constant should have this magnitude rather than any other. It is simply inserted by hand, a cosmic fudge factor dressed in mathematical notation. This bothers physicists. It bothers them not because the model fails to fit the data, it fits beautifully, but because it fails to explain. A model that works without explaining why it works feels incomplete, unsatisfying, perhaps fragile. Evolving dark energy, by contrast, offers at least the possibility of explanation. If dark energy is a scalar field, then its value at any given time is determined by dynamics, by the shape of its potential energy function, by the initial conditions when the field started rolling, by the interactions it has with other fields. These are things that might, in principle, be calculated from a more fundamental theory. Quintessence does not require arbitrary fine-tuning in the same way lambda CDM does. This does not mean quintessence is right. Many quintessence models have their own arbitrary features, the shape of the potential, the initial conditions, the overall energy scale. The problem of explaining dark energy is not solved by making it dynamic, but it is at least addressed differently. The mystery takes a different form, one that some physicists find more palatable, more amenable to eventual explanation. There is something almost philosophical about this preference. It reflects a belief that the universe should make sense, that its parameters should emerge from principles rather than being brute facts. This belief has motivated physics for centuries and has often proven fruitful. The search for underlying explanations has led to genuine discoveries. But there is no guarantee that the universe shares our aesthetic preferences. It may simply be what it is, with numbers that have no deeper meaning, with features that cannot be derived but only measured. The DESI results do not resolve this philosophical tension, but they reopen it. They remind us that the question of whether dark energy is a constant or a field is not just about fitting data. It is about whether the universe's most fundamental features are explicable or simply given, whether physics can ultimately explain everything or must eventually accept some things as brute facts. This question may not have an answer, or at least not an answer we can reach, but it shapes how physicists feel about their models, which in turn shapes how eagerly they seek alternatives, which in turn shapes which experiments get funded and which theories get developed. The philosophy feeds back into the science, and so the DESI collaboration continues its work. The spectrograph keeps splitting light, the robots keep positioning fibres, the data keeps accumulating. Night after night, the positions and redshifts of millions of galaxies are recorded, adding to a map that grows more detailed with each passing month. By the time the survey concludes, it will have measured over 40 million galaxies and quasars. 40 million points of light, each one a signpost marking the expansion history of the universe. 40 million opportunities to catch dark energy in the act of changing. The statistical power of the final dataset will dwarf what the first-year results provide. The error bars will shrink. The hints will either crystallize into discoveries or evaporate into noise. There will be no room for ambiguity, at least not at the current level. Either dark energy evolves or it does not, and the DESI final results will tell us which. But that data is years away from full analysis. The universe has been waiting 13.8 billion years. It can wait a few more. In the meantime, theorists explore the implications of both possibilities. If dark energy is constant, what does that tell us about fundamental physics? If it evolves, what kind of field could explain the evolution? If it crosses the phantom divide, what exotic mechanism could allow that? The parameter space is vast. The constraints are slowly tightening. Each new measurement eliminates some possibilities and leaves others standing. And here is something worth holding in mind as we wait for the data to mature. The outcome of this investigation will shape not just our understanding of cosmology, but our understanding of physics itself. Dark energy is not a peripheral detail. It dominates the universe's energy budget. It controls its fate. Its nature bears on questions about quantum field theory, about string theory, about the ultimate laws that govern reality. A measurement of evolving dark energy would ripple outward from cosmology into particle physics, into quantum gravity, into the deepest questions physicists can ask. The stakes could hardly be higher. And yet, the work is patient. It proceeds one galaxy at a time, one spectrum at a time, one tiny piece of evidence at a time. That contrast between the immensity of the question and the modesty of the method is part of what makes modern cosmology so remarkable. We are asking the largest questions humans have ever asked, and we are answering them by carefully measuring the colour of light from distant points of fire scattered across the dark. The largest questions humans have ever asked. That phrase deserves to sit with you for a moment because it is not hyperbole. When the DESI collaboration measures the positions of galaxies, when they extract the scale of baryon acoustic oscillations from the clustering patterns in their data, when they plot the expansion history of the universe across 11 billion years, they are doing something that would have been inconceivable to every generation of humans before the 20th century. They are taking the measure of everything that exists. They are weighing the invisible. They are asking what the cosmos is made of, how it will end, and whether its fundamental properties are fixed or flowing. These are questions that philosophers have posed for millennia, that theologians have wrapped in doctrine, that poets have circled in metaphor. And now they are being answered by robots positioning optical fibres in the cold desert air of an Arizona mountaintop. The distance between the question and the method is vertiginous. Consider what is actually happening when DESI collects a spectrum. A photon leaves a galaxy. It travels for billions of years through the expanding void, its wavelength stretching as space itself stretches, carrying information about the conditions at the moment of its emission. It passes through intergalactic space, through the cosmic web, past filaments of dark matter and pools of hot gas. It continues for eons, crossing distances that render human scales meaningless. And then, in the final fraction of a second of its journey, it passes through Earth's atmosphere, enters the dome of a telescope, bounces off a mirror, travels down an optical fibre thinner than a human hair, and lands on a detector that converts its arrival into a number stored in a computer. One photon, one number, one infinitesimal piece of evidence about the expansion of the universe. Now multiply that by billions. Billions of photons from millions of galaxies, each one carrying its own piece of the story, each one a messenger from a different point in cosmic history. The DESI spectrograph collects them all, sorts them, measures their wavelengths, computes their redshifts, and adds them to a growing map of the universe's structure. The map is not a picture. It is a three-dimensional reconstruction of where matter was at different epochs, how it clustered, how the clustering evolved, how the scale of the universe changed over time. From that reconstruction, physicists extract the expansion history. From the expansion history, they infer the properties of dark energy. From the properties of dark energy, they constrain the fate of everything. The chain of inference is long. The opportunities for error are many. A systematic misunderstanding of how light travels through the atmosphere could corrupt the results. A subtle bias in how fibres are positioned could skew the clustering measurements. An incorrect assumption about how galaxies trace dark matter could propagate through the analysis and emerge as a spurious signal. The collaboration knows this. They spend years checking their work, testing their pipelines, simulating fake universes and running their analysis on the simulations to see if they recover the correct answer. They blind their analyses, hiding the key numbers from themselves until the final moment to prevent unconscious bias from creeping in. They publish their methods before they publish their results, inviting the community to criticize their approach while there is still time to change it. And still, despite all these precautions, the results are uncertain. The 2 sigma preference for evolving dark energy is real. It is not a mistake, but it is also not a discovery. The error bars are wide enough that a cosmological constant remains consistent with the data. The phantom crossing hints are intriguing, but depend sensitively on how the equation of state is parameterized. The full picture will not emerge until the survey is complete, until the statistical power has increased, until the systematic errors are better understood. The collaboration has been clear about this. They are not claiming to have discovered new physics. They are claiming to have found hints that warrant further investigation. But those hints are remarkable nonetheless. For over 2 decades, the cosmological constant has stood unchallenged. Lambda CDM has fit every major data set. The dark energy equation of state has been measured repeatedly, and every time it has come back consistent with -1. The concordance model has earned its name. It has unified observations from the cosmic microwave background, from supernova, from baryon acoustic oscillations, from weak gravitational lensing, from galaxy cluster counts. No other model in the history of cosmology has been tested so thoroughly against so many independent lines of evidence, and no other model has passed those tests so consistently. Now, for the first time in a generation, there is a crack in that consistency. The DESI results, combined with supernova and CMB data, prefer a model in which dark energy was stronger in the past and is weakening toward the present. The preference is not overwhelming, but it is present. It shows up in multiple analyses, with different datasets, using different statistical methods. It is not going away. And here is what that means, if it holds. The cosmological constant, the simplest explanation for cosmic acceleration, the explanation that Einstein introduced and then called his greatest blunder, the explanation that was resurrected in 1998 and has reigned ever since, may be wrong. The universe may not be governed by a fixed energy density of empty space. It may instead be governed by a dynamical field, a substance with its own physics, its own equation of state, its own evolution. The implications cascade outward from that single change, like ripples from a stone dropped into still water. A dynamical dark energy field would require new fundamental physics. The standard model of particle physics does not contain such a field. The Higgs boson, the only scalar field we have directly detected, does not have the properties needed to drive cosmic acceleration. If dark energy is a field, it is a new field, something we have never seen in an accelerator, something that interacts so weakly with ordinary matter that it leaves no trace in laboratory experiments. It would be the second great invisible component of the universe, alongside dark matter, detectable only through its gravitational effects on the larger scales. That invisibility is troubling. If dark energy is a field, where does it come from? What determines its potential energy? Why is its energy scale so incredibly small, 120 orders of magnitude smaller than naive theoretical predictions? These questions were already acute for the cosmological constant. They become even more pressing for a dynamical field, because now you have to explain not just the smallness, but the time evolution. You have to explain why the field is rolling down its potential in just the right way, at just the right rate, to produce the acceleration we observe today. You have to explain why we happen to live at the cosmic epoch when the field's energy density is comparable to the matter density, even though those two quantities evolve completely differently over time. This is the coincidence problem, and it has haunted dark energy physics since the beginning. Matter dilutes as the universe expands. Radiation dilutes even faster. But a cosmological constant does not dilute at all. Its energy density stays fixed. So why, out of all the possible epochs in cosmic history, do we live at the one epoch when dark energy and matter are roughly equal? If we'd been born a few billion years earlier, matter would have dominated overwhelmingly. A few billion years later, dark energy will dominate absolutely. Only now, only in this narrow window are they comparable. Is this a coincidence? Is it a selection effect? Are observers more likely to arise during this transition epoch? Or is there some dynamical mechanism that links the two, that causes dark energy to track matter for a while before pulling ahead? A dynamical field can, in principle, ease the coincidence problem. Some quintessence models have tracking solutions, where the field's energy density follows the dominant component for much of cosmic history, before eventually taking over. These solutions are not automatic. They require specific choices of the potential, but they exist. They transform the coincidence from a brute accident into a consequence of dynamics. Whether the DESI-preferred evolution corresponds to such a tracking solution is an open question. The data are not yet precise enough to distinguish between different theoretical explanations, but the fact that the data prefer any evolution at all is already a clue that the coincidence problem might have a physical answer rather than an anthropic one. There is another possibility, darker and stranger. What if dark energy is not a field at all? What if it is a sign that general relativity breaks down on cosmological scales? Einstein's theory has been tested with exquisite precision in the solar system, around pulsars, even in the collision of black holes. But all those tests probe scales far smaller than the cosmic horizon. On the larger scales, where dark energy dominates, general relativity has been tested less thoroughly. It is at least conceivable that the observed acceleration is not due to an exotic energy component, but to a modification of gravity itself. Modified gravity theories are difficult to construct. They tend to introduce new degrees of freedom that cause problems elsewhere. ghosts, instabilities, conflicts with solar system tests. But theorists have developed classes of modified gravity models that evade these problems, at least so far. If the DESI results hold up, if dark energy really does evolve, some of those models will fit better than others. The data will begin to discriminate not just between constant and evolving dark energy, but between evolving dark energy and modified gravity. Each possibility leads to a different set of predictions for structure growth, for gravitational wave propagation, for the relationship between matter clustering and light bending. The next generation of surveys will test those predictions. You see how the stakes compound. A single measurement, the position of the acoustic peak, the redshift of a galaxy, the shape of a supernova-like curve, feeds into an analysis that constrains the expansion history, which constrains the dark energy equation of state, which constrains the fundamental physics governing the universe. The chain is long, but every link is forged from careful observation, and at the end of the chain the questions become as deep as any humans have asked. What is space made of? What laws govern reality? Will the universe end in heat death, in a big rip, in something stranger still? The DESI collaboration cannot answer those questions with their first-year data, but they have taken a step toward answering them. They have shown that the question of dark energy's nature is not closed. They have demonstrated that the data have enough power to distinguish, or soon will, between a universe with a cosmological constant and a universe with something else entirely. They have reminded the community that the concordance model, for all its success, remains provisional. Science does not end when a theory fits the data. It ends, if it ever ends, when there are no more questions to ask, and there are so many questions left. What happens if the phantom divide is real? What happens if dark energy's equation of state can cross below -1? The theoretical implications are severe. A cosmological constant has W equals -1 by definition. It cannot cross. A canonical scalar field rolling down a smooth potential has a greater than -1 by construction. It cannot cross either. To cross the divide, you need something exotic. Multiple fields with different properties interacting in just the right way. Or a single field with non-standard kinetic terms that allow it to behave differently than ordinary matter. Or a modification of gravity that mimics the behavior of crossing without actually requiring a physical field. The DESI data hint at crossing. They do not demand it, but they permit it. And that permission alone is enough to fuel years of theoretical work. The physicists who study these possibilities are not constructing fantasy worlds. They are constrained at every step by consistency, by the requirement that their models not produce ghosts or instabilities, that they recover general relativity in the regimes where it has been tested, that they make predictions for future observations that can be checked. The space of allowed theories is not infinite. It is bounded by mathematics, by symmetry principles, by the requirement that nature hang together in a coherent way. The DESI data tighten those bounds further. They eliminate some possibilities and leave others standing. The survivors become the focus of attention, the subjects of papers, the targets of the next round of observations. This is how physics advances, not through revelation but through elimination, not through discovering what is true but through ruling out what is false. Each measurement, each observation, each carefully analysed dataset removes another region of possibility space, leaving behind a smaller and smaller domain where the truth might reside. The domain is still large. Dark energy physics is still young, but the boundaries are closing in, and DESI is helping to draw them. Let this settle for a moment. We began with a survey. Robots and fibres and spectrographs and mirrors. We followed the light from distant galaxies, traced the patterns in the cosmic web, extracted the scale of ancient sound waves frozen into the distribution of matter. We compared those scales across different epochs and found that the expansion history deviates, slightly, tentatively, but measurably, from what a cosmological constant predicts. We explored the implications, the possibility of quintessence, the challenge of phantom crossing, the breakdown of the concordance model, the questions about modified gravity and quantum field theory, and the fate of the universe. The chain of reasoning stretched from the concrete to the abstract, from photons landing on detectors to the ultimate nature of reality. And through it all, the data remain paramount. The hints are only hints. The preferences are only preferences. The final word has not been spoken. The universe has been expanding for 13.8 billion years, and it will continue expanding long after the DESI survey concludes, long after the telescopes fall silent, long after the species that built them has vanished into whatever future awaits. The acceleration will continue. We are confident of that much. The distances between galaxies will grow. The cosmic horizon will shrink. The observable universe will become lonelier and darker with each passing eon. But whether that acceleration is driven by a constant or a field, whether it is strengthening or weakening, whether it will tear the universe apart or merely stretch it into cold equilibrium, those questions remain open. The DESI collaboration has given us a glimpse of an answer, a hint that the simplest story may not be the true one. That hint may be confirmed, it may be refuted, the data will decide. And so we wait, as humans have always waited, for the universe to reveal itself. We build instruments of increasing precision. We gather light from the edge of the observable cosmos. We compare what we see to what our theories predict. And when the predictions fail, even slightly, even tentatively, we pay attention. Because the failures are where the physics lives. The failures are where the next theory is born. Tonight, while you drift towards sleep, the Mail telescope continues its work. The dome is open to the Arizona sky. The robots are positioning fibers. The spectrograph is splitting light into its component wavelengths. Somewhere in that light, hidden in the patterns of absorption and emission, is the answer to one of the deepest questions humans have ever asked. What is the dark energy that fills the universe and drives its acceleration? Is it fixed, eternal, unchanging? Or is it evolving, dynamic, a field with its own history and its own future? The answer matters. It matters for physics, for cosmology, for our understanding of space and time and matter and energy. But it also matters for something harder to name. It matters for the story we tell ourselves about what kind of universe we inhabit. A universe with a cosmological constant is strange but stable. The laws are fixed. The energy density is set. There is nothing more to discover about dark energy, only its value, which we have already measured. A universe with evolving dark energy is different. It is a universe in flux, where even the most fundamental properties are changing, where the rules themselves are part of the unfolding history. That universe is less settled, less finished, more mysterious. We do not yet know which universe we live in. The DESI results suggest we should take seriously the possibility that it is the second. That the dark energy driving cosmic acceleration is not a constant but a field. That the field is rolling down a potential, its properties shifting over cosmic time. That the universe's fate depends on the shape of that potential, on the dynamics we have only begun to measure. Picture the universe once more, not as it is now, but as it may be in the deep future. If dark energy remains constant, the expansion will continue forever, slower and slower as the remaining matter dilutes to nothing, until the cosmos is a cold, dark, empty expanse with nothing left to change. If dark energy strengthens, the expansion will accelerate beyond all bounds, tearing apart galaxies, then stars, then planets, then atoms, in a final catastrophic unravelling. If dark energy weakens, something else may happen. A recollapse, a bounce, a transition to a different cosmic phase. The fate of everything hangs on the slope of a potential we cannot yet measure. The DESI collaboration is measuring that slope. They are doing it one galaxy at a time, one photon at a time, one fibre positioned in the Arizona darkness at a time. The work is patient. The progress is slow. But the question they are answering is the question that has always haunted humanity. Whenever we looked up at the night sky and wondered what was out there and what it meant. What is the universe made of? How will it end? And are we alone in asking? The last question cannot be answered by spectrographs and surveys. But the first two are within reach. The data are accumulating. The analysis is ongoing. The answer is coming, carried to us across billions of light years by photons that left their source galaxies before the Earth existed, before the sun ignited, before the atoms in your body were forged in the cores of dying stars. Those photons arrive tonight. They land on detectors in the Arizona desert. They become numbers in a database, points on a plot, evidence for or against the simplest model of the cosmos. And in their patterns, hidden beneath the noise, may be the signature of something new. A field that pervades all of space, that changes with time, that determines the ultimate fate of everything that exists. We are not yet certain. We may never be. But the search continues, as it always has, one observation at a time. The universe has been waiting 13.8 billion years to reveal its secrets. It can wait a little longer, and so can we, drifting now towards sleep, towards silence, toward whatever dreams may come, while the telescopes keep watching, and the light keeps arriving, and the questions keep asking themselves into the darkness.